The epoxide synthesis. So actually, I'm going to give everybody a headache that watches this online. We talked about reactions for our epoxides, both making them either from a halohydrin, which we talked about that reaction in detail, or from MCPBA, which I ran through that mechanism really, really quickly. And we'll go through that a little bit slower today. Okay, so those are our two ways to go through and make epoxides. Epoxides are pretty cool because we have that stressed three-membered ring. And that stressed three-membered ring wants to break open. How it breaks open can be controlled based on the reagents that we add. So that's kind of a neat thing with it. Here was our epoxide synthesis through the halohydrin. We talked about that already, so I'm going to skip over that. There's our synthesis, if you want to try and look at that again. And then the epoxide one. Okay. I didn't have time to go through and clean this one up a little bit. So let's take a closer look at our overall mechanism. And actually scratch that, we're going to do it slightly differently. Everybody seems to be getting bogged down in the arrow pushing for the epoxide. It is really kind of complicated as far as the arrow pushing goes. So when we look at this, you should just remember MCPBA, alkene, epoxide. Focus on that and you're okay. The next question is, where does the oxygen come from within the MCPBA? And a lot of people have panicked on that. Right, we've got our alkene with those p orbitals that can be potentially filled with electrons. So what we end up doing is ripping the oxygen out of our MCPBA structure and just giving it to the p orbitals. If we do that, we now have the epoxide. Okay? We could look at each of those bonds within it. Oxygen is most likely going to take electrons away from the hydrogen, and it's most likely going to lose them from the other oxygen because the other oxygen is resonance stabilized. So that oxygen has both a source of electrons and a lacking of electrons, which is why it can react really well with the pi bond, because the pi bond has the exact same issue. It's got the positive charge and the negative charge within the resonance structure of our pi bond. Okay? So, one last time, let's take a look at the mechanism all the way through. When we look at this reagent, we should focus on its instability. And I would make an argument that the most unstable thing within that structure is the oxygen-oxygen bond. Right, both those oxygens are now vying for the same electron density. And just like we saw with halogens in their elemental state, bromine or Br2, bromine-bromine bond, that bond breaks open pretty quickly with light. Same thing's going to happen with our peroxide. So what ends up happening is our uppermost oxygen steals those electrons. Okay? That leaves our oxygen electron deficient. Okay? So to help that process, our pi bond can share electrons upwards to that oxygen. Say, hey, I can share some electrons with you so you can break that other person off. Okay? In the process of doing so, we then mean that we've formed too many electrons on our carbon, so we have to then push electrons from that pi bond onto our oxygen. Okay? The next part of this is kind of the tricky one, and why it actually looks kind of interesting, is that that oxygen can share its electrons with the hydrogen. What we've got in that case is a 5-membered transition state. Okay, 5 atoms all arranged in a ring. Well, a 5-atomed transition state is okay because cyclopentanes are relatively stable. So we don't get a lot of ring strain on that. Then our hydrogen has too many electrons, so it shares its electrons back with the oxygen/carbon. The net result is that we convert the pi bond into 2 sigma bonds with our oxygen, and we've now got our epoxide. The biggest lesson out of this is that all of this is happening at the exact same instant. How do we know it's all happening at the exact same instant? What's that? We went to the lab, and in the process of looking at the results in lab, what we find is that we don't get a switch up in the stereochemistry of the groups on our alkene. So if our alkene starts trans with our R groups on opposite sides, when we go through to make the epoxide, and we add, say, an R group here, where's the other R group? It's still in that same trans position. It does not change. Okay? Our mechanism shows this, but the only way we could figure out our mechanism was take a guess at it, go into lab, and see what the result was. Okay, so based on our result in lab, the maintenance of that stereochemistry, we end up with that exact same result. Okay, or we end up with that mechanism as our answer. So the mechanism is derived from the lab, from what we see in lab. Questions about that? Yes, okay, as I clicked forward, that's okay. What's up?
How can we have from here to here?
The relationship between the last two structures. What's going on there? Those are attempting to show the same thing. Okay, depending on what we're looking at, we may see these drawn in slightly different formats. Okay. We are sort of implying that those back bonds are dashed away, okay, and that the other ones are in the plane of the board. Okay. Yes, it looks a little bit weird, but you may see it that way. So they're sort of implying stereochemistry in that fashion. The best way to go through and show it is that first structure, because that first structure much more appropriately signifies the wedges and the dashes in the appropriate stereochemistry and positions. You may see an epoxide with the double dashed, or the double wedged oxygens. Okay? They're just trying to show its relative position to the rest of the structure.
So they are not enantiomers.
What's
They are
that?
not,
We're not looking at enantiomers in this case. We'll talk about enantiomers with epoxides in a little bit. Yes.
So would we potentially see that second structure on an ACS exam? though?
Yeah. Yeah,
And
you would.
do we always assume that those back
And actually, I forgot.
are wedged?
Technically, everything is wedged. What we're saying is that oxygen is coming out directly out of the board at you, and because it's a planar molecule, all of those carbons are now technically away. They can't be in the plane of the paper because those carbons are sp3 hybridized. We need that tetrahedral structure. So what we've done is taken be really beneficial for anybody watching it online. Okay. So, side note, this is kind of a fun system with our epoxides. Epoxides, as relatively clearly states up there, are formed from the reactions of alkenes. Okay, what's the issue with reacting alkenes? Has to do with stereochemistry, yes. If I drew an alkene. Nope. Where can the epoxide form? Above or below, which means two products. We end up with enantiomers in our products. So all alkene reactions have the potential to give you enantiomeric products. Okay? We have to say potential because it depends on what else is attached to the alkene. If I went through and made these all hydrogens, then I don't have to worry about an enantiomeric product because I get the exact same result. So be aware when you look at epoxide reactions, almost always there is stereochemistry that necessarily implies that there are two products formed. Okay, so you have to be a little bit careful with that. That's kind of what this slide is going through and showing. We're looking at the pi system of this compound, which I don't want to attempt to name, and our p orbitals are above and below the plane of that drawing. If they're in that above-below position, then when I form the epoxide, my oxygen from my MCPBA can settle in from the top, or it can settle in from the bottom. That's going to end up with two possible products, with two possible results. Okay, the relationship between those products will be that they're enantiomers. Okay, which means if we do an epoxidation reaction with an alkene, and we do expect two products, what should the optical activity be? What's that? 0. Right? Because one enantiomer gives you one rotation, the other one gives you the other rotation. Because there is no favoring one way or the other, we get a 50-50 mixture. So we get 0 optical activity, and it's also known as a racemic mixture. Okay? So that's kind of a neat or unfortunate side effect of our epoxides. unfortunately for you, sort of, you probably won't ever see this. This guy, by the last name was Sharpless, I think is actually true, came along and he invented a new reagent. This reagent forces one epoxide enantiomer over the other. So what he ends up doing is you take this titanium compound and then this DET compound. Okay? DET has some stereochemistry associated with it. It's either plus or minus. That configuration, when then put into a standard epoxide reaction, forces one enantiomer over the other. Okay? So in almost every reaction we've ever done, we have a way to make it very selective for a particular enantiomer. We just have to add a bunch of crazy stuff to it to go through and do that. Right? So your textbook mentions this, at least I think it mentions this. Don't stress too much about it. All they're trying to do is go through and say that when we do these reactions, we have to watch out for stereochemistry. Most cases, what we do in the lab, we lose that stereochemical control, okay, unless we invent some special catalyst to go through and do that. Okay. Is there another way we can go through and do these reactions without inventing a special catalyst? It's worse. Nearly everything in biology is chiral. Meaning if we look at our DNA, it's all one form. If we look at our proteins, they're all one form. They're all one hand or the other very, very particularly. Biology is chiral, which means if we want to go through and run one of these reactions, biology probably already does it. Right? And they do it, or it does it, very, very particularly. Right? How does it go through and do it? Okay, if you envision scissors. Any left-handed people in here? Oh, one person. How much did you like dealing with right-handed scissors? Yeah. Anybody use left-handed scissors, other than clearly the only left-handed person?
My husband's left-handed, so yeah.
Yeah, how comfortable is that?
Very good.
Yeah. So our scissors are designed to fit in right hands or left hands. And if we try and switch it, it becomes very uncomfortable. So what we can go through and do, and it's, no one ever believes me, but pick up a pair of scissors. Well, left-handers believe me. It's just shaped to fit your hand. And that's because your hands are chiral. So the way we can envision biology, or what's happening in biochemistry, is that we have a very stubborn left-hander or a very stubborn right-hander. So when it comes to trying to cut something, if they don't have the proper scissors, they don't do it. That's what's happening within biology. With organic chemistry, we don't have that selectivity. We just have a knife. Okay, so we can just cut things straight open with a knife. We don't really care what hand is holding it. Okay? So it's that same kind of concept. It's kind of neat, but at the same time, if you want to go through and run a reaction that's very selective, as say in biology, you would then have to go through and isolate whatever that compound was out of the biological system, which is a whole entire process in itself, potentially resulting in just a PhD on its own. Okay? Never mind actually getting it out to do whatever you wanted to do. Okay? So it is a very tedious process. A lot of organic chemistry is starting to push into these types of reagents because we want that selectivity, we want that control, and we just don't have it. So, getting into epoxides on why we want them or what we can do with them. Epoxides show up everywhere, so they are pretty big precursors as far as biomolecules. So I listed a whole bunch in here. I think you've got a derivative of cholesterol there up in number 2, or a steroid, I guess I should say. You've got some fatty acids and stuff like that showing up in there as well. Okay, so they are biologically relevant. So the question then becomes is what can we do with these biologically relevant molecules? Okay, so what we're going to look at is on the far right for these next few slides, looking at different conditions under which we can react these epoxides. Okay, and you'll notice right off the bat what's interesting about this epoxide. I know, it's kind of a weird question.
The ring is not stable, right?
The rings are naturally not super stable. They are fairly reactive, but they're stable enough that they'll exist.
Are you talking about the 2 boxes in the third job?
Yep. That one on the right is drawn a little bit weird, so we can ignore that one.
It's just the way.
So let's take a nucleophile, strong nucleophile. What charge is our strong nucleophile? Negative. So it's negative, so we know it's strong. All right, what does that negative want to find? Positive. Where's the positive? The carbon attached to the oxygen. I agree with that too. Except how many carbons are attached to the oxygen? There's 2. Why is this interesting? Are those carbons the same?
No.
No. Okay, in one case we have an R group attached, in the other case we have just hydrogens. So those carbons are now drastically different as far as their chemistry goes, which means when the nucleophile comes into attack, it's now going to have a choice between those. Is it selective for one over the other? We would kind of hope so, because that allows us to predict a little bit better. We also kind of hope it isn't, because then we don't have to predict as well. But what ends up happening is it is very, very selective.
Isn't it dependent on what the R group is, though, too?
Kind of, sort of, yeah. To a secondary effect. So let's not go to the secondary effect. Let's do the primary effect first.
This depends on the nucleophile.
Nope. What would we predict to happen? The nucleophile is going to attack one of those carbons, right? Which means it's going to form a new bond, which means that carbon would have too many electrons around it. Which then means what? It has to break a bond. So it's going to have to break one of the bonds to the oxygen. It won't break any of the others because you're right by saying it can't, but why? The bonds to the oxygen are the weaker ones because oxygen is more electronegative. It's already pulling those electrons away. None of the other R groups or hydrogens can go through and do that. So those are going to be our best bonds to go through and break. Okay? So let's go ahead, just for the sake of argument, and say it breaks the one on the right. Okay, what happens? The oxygen has the electrons. It becomes O negative. What type of reaction occurred around that carbon? Okay. If it's an elimination, we'd see a pi bond. We don't see a pi bond forming. If it's an addition, we'd also see a pi bond. We'd see the pi bond disappearing. Okay. What we have at that specific carbon, and this is one of the reasons why I circled just that carbon, because both the addition and the elimination need 2 carbons, we have a substitution. We traded an oxygen bond for a nucleophile bond. It's strictly a substitution. Okay. Now the question becomes is which mechanism happened at that carbon? SN1 or SN2? Why SN2? We have to look at the reagents that we've got supplied, and we have a strong nucleophile. When we look at our substitution reaction, remember there's 4 things we evaluate. Substrate, leaving group, nucleophile, and solvent. Solvent's not supplied. Leaving group is pretty horrible to begin with. But then we have the substrate, okay, and I'm saying we're just attacking that position anyway, so that disappears from it. All we really have, man, I can't really hold that finger up, is the nucleophile as our determiner. When we look at the SN1 versus the SN2 reaction, what determined our strength of our nucleophiles? That's how I counted them out. SN1 favors what type of nucleophile? Weak. SN2 favors strong. What do we have? A strong nucleophile, which suggests which mechanism? SN2. Which suggests which substrate? The less hindered substrate. So primary over secondary and never tertiary. If we now take that information back, so what we did is guessed at what our product would be, decided it was a substitution reaction. Now that we know it's a substitution reaction, we know there's 2 mechanisms. Based on those 2 mechanisms, we decided it was SN2 because of our strong nucleophile. That now takes us all the way back to our initial question, which carbon should the nucleophile attack? Which is dependent on the substrate. Since it's an SN2, we said it should be the least hindered position. Which carbon is the least hindered?
This one.
Oh, look at that, the one we circled to begin with. So what does that mean? Our nucleophile should attack that position preferentially. And that's exactly what we end up seeing with our epoxides. When the epoxide comes through and attacks, or when the nucleophile comes in and attacks, if it's a strong nucleophile, it does a backside attack on our epoxide, causing the O, or the oxygen, to leave. Oh, good thing I went through and balanced that out. We wouldn't have the hydrogens yet. Be negatively charged. A backside attack, and our nucleophile is attached to the least sterically hindered position. Okay. We could then follow this reaction up with what? Noticed a lot of people missing this when I was talking to them about the synthesis question. What would we follow this reaction up with? We could do water or H3O plus, either's fine. And we'd end up with our alcohol and our nucleophile potentially attached to it. Okay. So our epoxides become pretty cool because we end up with the alcohol, but we also have the ability to have now attached some nucleophilic species, which could be just a long carbon chain, or it could be another functional group or another oxygen. There's a variety of ways we could go with that. So in this case, what we're doing is just adding a strong nucleophile. How do we know it's strong? It's negative. How do you know it's a nucleophile? Come on, you can give me more than it says it is. What other piece of information allows us to know that that's a nucleophile?
The electron pair.
It has a pair of electrons. So pretty much anything with a pair of electrons can act as a nucleophile and cause our epoxide to break open. Okay? Questions about that? Okay. What happens? Yes?
It would never attack the other carbon because it's...
Under these conditions, it will not attack the other carbon. So when we're under basic or neutral conditions, and we have to specify basic or neutral because that's how we can get a strong nucleophile. If we made it acidic, what happens? We have H+. What does the H+ do? Goes right to the nucleophile, and now we don't have a strong nucleophile. So the reaction we just looked at was specifying under basic conditions or under neutral conditions with a strong nucleophile. We no longer have that strong nucleophile. Our whole argument for why it attacked the least sterically hindered one was because it was a strong nucleophile. If it's no longer strong, we're going to have to change our understanding of it. All right, and that's what these next conditions are under. If we go under acidic conditions, now things switch up. Okay? If it's under acidic conditions, and this is where I'm trying to get you to think about what happens as far as reactivity. If it's acidic, what does that mean is present? H+. What is that positive going to want to find? A negative. What's the most negative thing it could find?
Oxygen.
It could go for the oxygen, or it could go for a strong nucleophile. So you'll notice I did not specify a strong nucleophile in this reaction. Okay? So if it goes to the oxygen, what happens? Now when we look at our intermediate, we have something very similar to what we had in the previous case, except we now have what for a leaving group? A really good leaving group. And we also have a very weak nucleophile. So that leaving group is so good that it's already saying, I don't want to be here. I want those electrons. Where is it going to take those electrons from? Which bond? To the carbon. We then run into the same question we had before. Which carbon do we take the electrons from? Why would we take the electrons from the more substituted? What charge starts to build on the carbon? Positive. How do we stabilize that positive charge? we need more substituted things around it, more carbons to stabilize it. So our nucleophile is now going to react with the most positive atom being the more substituted carbon. It still goes through a backside attack, because that bond doesn't quite want to break off on its own, so that oxygen does kind of hover up there and block the other attack. But we will have that nucleophile now attach, whoops, well, actually, it's about to show it in the next slide anyway. We'll have our nucleophile go through and attack the least substituted position. Sorry, you're right, most substituted. That's what happens when you try and draw at the same time. Attacks our most substituted position, and we end up with our alcohol as our final product, and you'll notice the alcohol ends up on the other carbon, on our least substituted position. The nucleophile is on the most. The stereochemistry that comes out of this is dependent on the stereochemistry of the epoxide. Hi? Questions? Let it settle in a little bit more. Are we good? Okay, moving on. Yeah, that's what I figured. That's why I didn't do anything.
So that's SN1 or SN2?
So which mechanism are we going to be looking at? So this is where we do run into some oddities with this. It isn't really officially a substitution reaction either. We're running in this weird gray area. So in the previous case, under basic conditions, we could pretty much say it's an SN2. We could also go through and say it's an addition reaction, which is, I know, even weirder for people, except what do we have? We have an oxygen that has 2 bonds to a carbon. That looks an awful lot like a carbonyl. So for all intents and purposes, our epoxide acts the same way as a carbonyl does, except it's just different carbons. Okay? So we could call it an addition reaction as well. It's what you choose to focus on. In the SN2, or our basic conditions, we could kind of, in my opinion, very clearly see that as an SN2. Where I think you're going to debate me, though, is calling this an SN1. Because in the SN1, what do we form? Carbocation. Do we ever form a carbocation? No. It never officially forms. We end up having the nucleophile attack the most positive position because the leaving group already is itching to get off of there. Okay? So we never officially form the carbocation, which means we don't get a mixture of the products if we start with this particular stereochemistry. So what we're saying is that this approximates as best we can the SN1 mechanism. And that's really driven by we're forming pseudo-carbocations. Okay, does that make sense?
It's just kind of leaning in that direction when they
Yes. So when we talked about first semester, it was either SN1 or SN2. And it was a very clear black and white line. Turns out it's not black and white. It's like the rainbow. We've got this nice, beautiful spectrum, and somewhere in between we say, no, that's SN1 or that's SN2. It doesn't work that cleanly. What we're looking at in this case is something that approximates an SN1 with SN2 characteristics. The SN2 characteristic being backside attack, okay, which is sort of a mechanism.
When we did the bromonium ion, it forms that, then it kind of leans and the other one attacks. Is that a similar situation?
Similar situation. We have a very good leaving group, and when we saw the bromonium ion, our nucleophile attacked the most substituted position. It's the exact same situation. Okay? Other questions? Yeah.
If it's a oxide attack, that means we have the inversion of the configuration.
About that carbon? Yes.
Beyond that carbon.
Yeah.
So the R should be dash?
No. So this is something I've noticed as well. Let me actually switch up to a whiteboard here, clear all this away. If we go through and look at, let me switch that around. Let's make that a good leaving group with our water. hydrogen, deuterium. Would we expect SN1 or SN2? Why SN2?
Secondary carbon.
We have what kind of a carbon?
Secondary.
Again, it's primary. There's only one carbon attached to it. With the primary carbon, we expect this to go under an SN2 mechanism. So we would expect this to come in, attack from the backside, and we'd see the OH2 leave. Okay? This comes as a perspective for how you would go through and draw things. We could go through and assign R and S stereochemistry on this, and then we could look at the product and just make sure that the product does the opposite of it. I would argue that that is way more work than necessary, because you have to assign stereochemistry on this, then you have to assign stereochemistry on your product. If we're going to go through and do inversion, what happens? Where should the bromine bond be? So let's draw that bond first for the product. Based on this orientation.
Does that mean when that bromine comes in, everything flips up?
Yep, that's what we're getting to. Where should I draw the bromine bond? All right, we're not getting any volunteers, so let's go ahead and call this our carbon atom. It's our center carbon atom. Where should it be?
On the plane of the carbon?
Where? Left, right, up, down?
The bottom?
Should go downwards. There's our bond to our bromine. Okay. Here's where people have issues when we go through and deal with this in sapling. What I would argue you could go through and do is we're just swapping out from the backside. Don't touch anything else. Whoops. And then we'd have our OH up here. Sapling, and rightly so, probably does not give you credit for this answer. Right? All we've done is directly just done the substitution. Where the bromines come in, it's now on the bottom, OH is out the top, done. We've done the substitution. We've even shown the proper stereochemistry. However, what ends up happening? As Carlos was alluding to, what we're doing is we have to invert. The umbrella pops. So when the bromine comes up from the bottom, it's coming up from the bottom of those three structures, and now those three atoms have to pop the other direction. That does not mean they flip over. That means that they literally just bend in their locations upwards, which my hand can't do. Which means if I want to draw this structure out, I will keep the bromine in that position, probably not that close to that structure. Let me try that again. No, I can't do that. My CH3 now needs to be going up, okay? Not perfectly up, but it's just spreading out from its sort of position. So it needs to be up here. What happens with the hydrogen and the deuterium? Same deal. They just need to pop upwards. I've now got the proper stereochemistry drawn. I had to change nothing other than just sliding these atoms upwards. That's it. What if we came in from the side? Came in from the right side? Same deal. Now push everything towards the left. All right, then there's no swapping of atoms, switching them, making one wedged and one dashed. Okay? We're going through and saying, well, now since I did this attack, this hydrogen's dashed, this one's wedged. And I know people like to do that. Okay? We could go through and draw this same product out with that skeleton. Okay? And I cringe every time I see this. But students are actually pretty good at doing it right. So if you get it right, then by all means, keep doing it. Now we swap the hydrogen and the deuterium, because we have to show the stereochemistry changed. But that's because we didn't actually show the way the structure changed. So if we don't show the way the structure changes, then we have to get really particular with the stereochemistry. So it's a question of which do you prefer to do. I prefer to show how the atoms actually move, and I will maintain that arrangement as best I can. All right? Minimize my atom positions, rotations of the structure. Because then I'm minimizing the amount of stuff that changes on my end, which means I minimize my mistakes. If I go through and just say, well, all I've got to do is swap these atoms, if I forget to swap those atoms, I'm now screwed. Okay, particularly if it's at step 1 of a multi-step reaction. Kind of makes sense? So as best you can, when you try and draw something out, draw it out in the best reflection of what the structure is actually doing. Minimize any kind of rotations as best you can as well. When it comes to an exam, if I asked you to draw the product of this, I would accept this answer. I would probably draw on it, you should draw this better, but that's about it. Right? Because you are showing the appropriate structural effects of where those atoms end up. You just didn't finalize it by taking it to the appropriate bond angles between them. Right? Is it critical to nail down the bond angles? Depends how high a grade you want. I mean, if you want a really high grade, yeah, you should be nailing down the bond angles perfectly, because that will help you understand how those structures react. Otherwise, you are really relying on tricks and memorization techniques to get you to the correct answer, which works, just not for me. Okay? Questions about what I just drew up? Okay, which I guess then takes us backwards. Questions about the acidic reaction? Everyone okay with that? You'll notice that what's drawn on there are only steps. I didn't actually finalize each of those. Okay. Our overall epoxide summary, you'll notice that I'm not a fan of the halohydrin synthesis, which is, I guess, fine, as long as the ACS test doesn't ask me anything about halohydrins. I pretty much remember epoxides as MCPBA, and I stick to that. Okay. You can do it with the halohydrins as well. The part that you need to then take a step further is what's happening under the basic or acidic conditions where the nucleophile attacks. Under acidic conditions, our nucleophile will attack the most substituted position. Under basic conditions, it attacks the least substituted position. That's our big summary off of those. And that comes from understanding the dynamics of what's happening within each of those cases. Questions on our epoxides?
Did you say that when it's a weak nucleophile, it is an SN1?
It pushes more the SN1, yeah. Probably the bigger tip-off is that you'll probably be under slightly acidic, well, you have to be under acidic conditions. Because if it's a weak nucleophile, it can't attack the epoxide because the epoxide has a horrible leaving group. Right? So if it's a weak nucleophile, it needs to be acidic conditions. Last thing that we want to talk about with our alcohols, this really does strongly lead into our carbonyl chapter. Your textbook, for some reason, places it squarely in the carbonyl material as opposed to in the alcohol material. We are looking at the synthesis of an alcohol through an addition reaction. We've done the addition already. Okay? We looked at addition to alkenes. That made alcohols. We also looked at addition to carbonyls to make alcohols. What was our nucleophile in that case? What was the reagent? If I made that a carbonyl and I want to turn it into an alcohol, what was the reagent I added? I added hydride. Hydride was my nucleophile. Okay, H minus. The reagent we could have added? Sodium borohydride. Lithium aluminum hydride. We're adding H minus as a nucleophile. Okay. The last reaction we want to talk about in making alcohols is again doing an addition reaction to a carbonyl, except the nucleophile in this case, in the case of Grignard's, is tricky one. Nope. Got the right idea. In the case of Grignard's, it is a carbon nucleophile. And this is where we should go, what? How do we get carbon nucleophiles? What charge is a nucleophile? Has to be a source of electrons, negative. How do we get a carbon to be negative? At this point, you really only know potentially 2 reagents, and they all revolved around the triple bond. Okay, we could either use acetylide, which was from that synthesis question. That gets us a carbon nucleophile. Or we use cyanide, which I shouldn't write out as CN. Let's do cyanide, which gets us the negative charge. So far this semester, there's only been 2 reagents or 2 ways we can get carbon negative. Okay? It's really not easy to get a negative carbon. Turns out that this reaction, well, because it's so difficult to do, that it gets named after the person that first invented it or the first discovered it, and that's Grignard. I don't remember what his first name was, okay? But his last name was Grignard, some old school chemist. So, how can we get carbon to be a nucleophile? How can it get electrons? How does oxygen get electrons? It removes electrons from the atoms nearby. How does it remove the electrons from the atoms nearby? Oxygen is more electronegative than hydrogen or carbon, so it can take those electrons and become negative. Well, if I'm going to go through and make a negative carbon, what does it need to do? It needs to be able to take the electrons from the atoms nearby. We tried that with our alkynes, with the triple bond, and the hybridization affected the acidity or its electronegativity that made the carbon more electronegative so that it could take the electrons away from hydrogen. Okay. What's the other option? Are there atoms with lower electronegativity than carbon or hydrogen? I know everybody's got it memorized, right? All of our metals have lower electronegativity. Right? When you look at the electronegativity trends, the highest electronegativity is fluorine. The lowest electronegativity is cesium. So pretty much anything that is a metal has horrible electronegativity. It does not want electrons. It will give them up very, very quickly. Which is why when we add sodium to water, what happens? Get this big violent reaction, because what does sodium do? Gives up its electron to hydrogen, actually. It gives it up to the hydrogen to form hydride, which then pulls off another hydrogen and forms hydrogen gas. The oxygen won't accept it because the oxygen's already stable with its electrons. Okay? So if we put in a metal, we could reasonably assume that the metal will give up those electrons. But it needs to be able to do it in a reasonable fashion, because if it does it uber violently, that's not going to be particularly fun to work with, particularly in the lab, which you guys will all be doing in the lab. Okay? So what Grignard ended up discovering was that he could expose particular organic compounds to metals, and their chemistry drastically changed. And that's where he generated the carbon nucleophile. The classic metal is magnesium. Right, there are other metals out there that do pop up in the book, and we will talk about them briefly. Lithium, so we can look at alkyl lithium reagents, and we can also look at alkyl copper reagents. The copper reagent we will save for the tail end of our carbonyl discussion, so you don't need to read about that. What you should be concerned about is the magnesium, or the alkyl magnesium reagents, okay, and how they will react with carbonyls. Okay, so we're trying to keep it simplified as much as possible. The lithium reagent does pretty much the same thing once it's formed, but the forming process is slightly different. Okay? So if we go through and take a look at this, our overall reaction is that we start with an alkyl halide, usually alkyl bromides, but you can see it with the chlorides, and I don't think you can see it with the iodides, but I'm not positive. Magnesium metal has 2 electrons. Okay, it's not looking at magnesium ion, it's magnesium metal. We add the metal to that alkyl halide. The metal intercalates, okay, which means it sits in between or works its way between the carbon and the bromine. What type of bond do we have between magnesium and bromine? It's an ionic bond. So we started with magnesium as a metal, and now we have magnesium as an ion. What charge does magnesium carry as an ion? Close. Won't quite give you a perfect score if you just tell me it's positive. What charge does magnesium carry? It carries a +2 charge. What charge does a bromide carry? -1. Uh-oh, our charges don't balance. Where does it balance? the carbon carries a -1. There's our nucleophile. Right? So what ends up happening, if we look at the bonds, the bond between the magnesium and the bromine spends most of its time with the bromine. The bond between the carbon and the magnesium spends most of its time with the carbon. Okay? We get an insanely reactive structure. As such, this compound, once it's actually made, actually kind of stacks upon itself to try and stabilize that negative charge as much as possible. So that ends up meaning that it is a very sterically hindered structure. Okay, so if it's sterically hindered, what does that mean about its reactivity? So we have a sterically hindered negative charge. If it's negative, what does that mean? Nucleophile or base. If it's sterically hindered, what does that mean? It's a base. Our Grignard reagents, first and foremost, will act as bases. Okay? They are relatively strong. If it acts as a base, can it act as a nucleophile? No, because it's killed its characteristics. So when we go through and work with Grignard reactions, we have to be very, very careful that we limit the presence of acids. Because if any acid gets in there, our Grignard reagent does an acid-base reaction. So let's say the presence of H2O. And we end up with what as a product? So as a hint, draw that all on. There's another hint. Draw on that hydrogen. We end up with a hydroxide. That species precipitates out. The hydroxide of magnesium is very insoluble, and we see it this white precipitate form. What happened to our carbon being a good nucleophile? It's now become completely useless. Okay? We're actually, not only has it lost its nucleophilic characteristics, but it's taken a step further. We started with an alkyl halide. Halides at least have some chemistry. What did we end with? Just benzene. So if anything, we actually destroyed altogether any possible chemistry coming out of this reaction. So we go through all this process to make an alkyl halide. We then go through to make a Grignard, and then we wasted it all and took us all the way back to the very, very beginning. Okay? So we really want to avoid the presence of any kind of acidic structures. Water's a big one. Okay? So, next part of this that I think is kind of interesting is looking at the mechanism. I will tell you right now, you are not responsible for this mechanism. Okay? The formation of the Grignard, you are not responsible. You are responsible for what happens once it's a nucleophile. Okay? So once we have that negative carbon, what can it do? That you're good for. You need to know that. For this part, not so much. Okay? So, when we looked at sodium metal, what does it end up doing? You guys remember that one? What does sodium metal do in a mechanism? Yeah, it gives up a single electron, okay, in a radical. Since we're moving one electron at a time, we've got the single electron transfer for our theory. When we're looking at magnesium, it does something very, very similar. It gives up just one electron. Okay, so what ends up happening is our magnesium gives up a single electron. Since we're moving only one electron, we look at it moving into the space between where a bond forms. Okay, the bromine sees that electron and says, hey, I can help out. So it takes an electron. But it's taking that electron away from the bond that it had with the carbon. Would we expect bromine to take that electron anyway?
Yes.
Yeah, it's not horrible. Okay, bromine is more electronegative. What happened to that other electron? What's that? It will act as a radical. It's still on the carbon. That's all true. That's where it should be. But does my mechanism show that yet? No. I need to show that that one electron made it to the carbon. How do I show that?
After
I start with a half arrow from that bond, which is where the electron was, and dump it onto the carbon. Okay, so with radical mechanisms, you've got a lot more arrows to go through and show. The net result is we've now formed a bond between the magnesium and the bromine. What type of bond? Sort of sigma. I don't quite accept sigma. Ionic. Okay, we now have an ionic bond between the magnesium and the bromine. And we now have two radicals. What can these radicals then do? They can pair up. And we've now got our final structure with the bond between the magnesium and the carbon, which is what type of bond? Sigma and ionic. That electron density spends most of its time on the carbon because magnesium is less electronegative than the carbon, or carbon is more electronegative than the magnesium. And what we end up with as an overall structure, at least for mechanisms, is you will almost always see, at least me, write it out this fashion. Why do I ignore the magnesium and the bromine? They're not organic, but more importantly, it's an ionic bond. Just like when we dealt with sodium hydroxide, what do we do with the sodium? We ignore it. Okay? So we now have our reactive nucleophile that could potentially go through and do some other chemistry. How did they actually settle on this reaction? Okay, I think this is kind of neat. One of the byproducts of this reaction is this structure. What compound is that? Biphenyl, because we've got phenyl rings. There's two of them, so it's biphenyl. Where did that come from? Two phenyl radicals reacting with each other. Okay? If we didn't have the phenyl radical, we don't have a way of making biphenyl. Okay? So the presence of the biphenyl suggests that we do end up with a phenyl radical. Without the biphenyl, we have no clue of the mechanism. Because we could potentially do homolytic cleavage, heterolytic cleavage of those bonds, generating charged species, okay, all the way through it, as opposed to single electron transfer. Okay, so kind of a neat reaction.
Is that bisphenol?
No, bisphenol is something else. It's bisphenol with an OL. You're looking at the alcohols on there. So you're probably, yeah, this is YL. The BPA is phenol with the P, which is a good point to bring up. Phenol is an OH. Then we also have phenyl with the YL. Okay, so be careful with that. Phenol, I try to pronounce it as differently as possible, but based on the reaction I get from students, I don't think anybody can hear what I'm hearing when I try and say the difference. Okay, which is fine. That's just attempting. So phenol with an O, phenyl with a Y. Okay, not to be confused with benzyl. Okay, or benzyl for that matter. Which is another one you can throw in there. YL versus IL. Okay? Nomenclature. So, carbon nucleophiles. So if we start with formaldehyde, we can have that nucleophile, whatever it may be, go through and attack our carbonyl. The carbonyl separates as a partial negative and a partial positive. Because we're working with a what type of nucleophile? Strong nucleophile, we don't need to activate the oxygen on our carbonyl. What's up? Nothing? Okay. So our nucleophile can attack our positively charged or partial positively charged carbon of our carbonyl, causing that bond to break open. We then end up with the carbanion. In this case, we can stall at the carbanion because there's nothing positively charged left. So it just kind of sticks with our, sorry, not carbanion, oxyanion. Okay? That negatively charged oxygen. We'll follow that up with a step 2. In the step 2, what do we add? Water or H3O plus, some kind of source of hydrogen, and that will protonate our oxyanion to give us the alcohol. What type of alcohol did we make? This one's primary, it's just got one carbon attached to it. Could we have changed and gotten a secondary alcohol? How could we have done that? No? What would we change on our product to make it a secondary alcohol?
One of the H's for an R group.
One of those H's needs to be some kind of R group, right? Where did that H come from? So what we did was swap that H for an R. Where did the H come from? We started with it on which species? Our formaldehyde. So what happens if I turn that H into an R? What happens when the nucleophile attacks now? I'd end up with secondary alcohol. What functional did I react? Functional group did I start with? An aldehyde. Related to formaldehyde, but slightly different. What if I want a tertiary alcohol? I need to swap out that other R group for a hydrogen, or other hydrogen for an R group, and we end up with what functional group? We now have a ketone. So depending on what carbonyl we start with, we can end up with a different type of product or alcohol product, be it primary, secondary, or tertiary. Okay, and I believe all of those are on here. So yeah, there's our secondary, starting with an aldehyde, and we've got our tertiary starting with a ketone. Okay? In each of those cases, you'll notice that H3O plus is added as a step 2. Okay? Step 2 means we see numbers. It's not listing out the number of reagents, but the number of steps. Why must we specify it as a second step?
Because you want to put it there initially.
No. If we added it all at once, what does the Grignard do? Acts as a base, pulls the hydrogen off, we don't have a nucleophile, we don't get our reaction to occur. Okay? What type of reaction did we do overall with all of these? It's an addition. What did we add? Carbon nucleophile and hydrogen. We added 2 things. That's what happens when we do our addition reactions. We always add 2 things to our structure. Okay? Stability of the carbon nucleophile versus reactivity. So if we look at this one, what would we expect to be our product? And real quickly, just kind of crank out a product there. So I know you all can draw real fast. Right? We get our tertiary alcohol. Cool, we just did a Grignard reaction. Fantastic. Good job. Okay, let's take a look at another one. What's the product in this case? So this is one that can be sneaky on your multiple choice. Whoa, come back here. We'll start with that quiz on Thursday. Ah, stop it. Because I'm yelling at the microphone. That's useful. Almost always you will see this answer on your ACS exam. That will be one of your answer choices. You want to know what the other answer choice is going to be? So that's A and this is B. And everybody's going to go, B can't possibly be the answer. That didn't happen. Grignard reagents are exceedingly reactive. They will react. The question is, what did they react with? In A, what did the Grignard reagent react with? The carbonyl. In B, what did the Grignard reagent react with? Technically not the alcohol. Phenol. Reacted with the phenol to make methane. All it did was pick up a hydrogen. Everybody skips over the CH4 because they go, oh, there's too many carbons. There's no way that can be the product. Reaction did occur, and that is exactly what the product was. The other thing really didn't do much. Okay? So watch out for those misleading answers when it comes to Grignard reagents. You have to evaluate the whole structure. Is there something else that's positive? It's not just the carbonyl.
So it will react.
It will react to form CH4. So our Grignard in this case reacts as a base, not as a nucleophile.
Does it
So in the
favor one over the other?
base first. So this is our Grignard acting as a base. The top one was our Grignard reacting as a nucleophile. So given the choice, it will act as the base before it acts as the nucleophile.
So it'll steal the hydrogen.
It'll steal the hydrogen. Yep. So your answer in that bottom case would have to be B.
That's because the hydrogen's more positive than the carbon at that point?
Yes, exactly right. And not only is it more positive, look at the sterics. Where's the hydrogen? On the outside of the structure. The carbonyl carbon is inside the structure. Okay, so that positive hydrogen is not only easily available, but also relatively positive. Okay, so watch out for that functional group issue popping up. One of the other things that we'll talk about on Thursday is, first off, we'll go through that quiz, which might be the last slide for Grignards, but I'll also address new functional groups. Esters. Okay, we already saw how esters reacted with hydride nucleophiles. Think about how carbon nucleophiles are going to react with them. Okay, it's a very similar process. Okay, I'm going to stop recording.